Now let's give the geometrical interpretation of gradient. So if a surface phi passes through a point P, the value of the function at each point on the surface is the same as that at P. So if a surface phi equals to C passes through a point P, then the value of the function at each point on the surface is the same as what we have at P. And such a surface is called a level surface through the point P. For instance, if we have phi of x, y, z, so if we have phi to be the potential at this point P, then the potential surface phi given by C is a level surface. And then one key thing that you have to remember is that no two level surfaces can intersect. So consider so let's draw some two, say this curve, and then these are the curve. So let's have a point P at this point. Let's have a point sub R. Let's have Q. So this is what you're calling phi equals to C. And then this is phi plus d phi equals to C. So we call this vector delta R. We call this vector delta N. And this is the unit normal. So this one surface is another surface. So let the surface level surface through the point P at which the value of the function is phi. So let the level surface pass through the point P. So you can see that in the sketch. So let the level surface pass through the point P at which the value of the function is phi. Consider another level surface. So this point Q. Phi plus d phi. So now let R be the position vector of P and let delta R be the position vector of point Q. Then the vector OP or the vector PQ will be given by delta R. So this is R plus delta. So the position vectors of point P and Q are R and R plus delta R respectively. So therefore, PQ will be given by delta R. So if you define the gradient of phi times the R, we get I partial phi partial x plus j partial phi partial y plus partial phi partial zk. And then we are dotting with, so the R by definition is given by I dx plus j dy plus k dz. So interpretation of the dot product means that we are going to get the product of the component of I, then sum to those components of j, and then those for k. So we'll have partial phi partial x dx plus partial phi partial y dy plus partial phi partial z dz. And you see, this is the interpretation of the differential of phi. So if Q then you expect this differential to be 0. So if I call this one equation 1, call this equation 1, then it means in that case whereby Q is lying on the same level curve of P, then one becomes that the dot product of gradient of phi and the R will be given by 0. So which means that this gradient of this function phi and the R are orthogonal, because the dot product giving 0 actually that's a confirmation that the two vectors are orthogonal or meeting at 90 degrees. So this simply means that they are tangent to each other. Hence, gradient of phi is the normal to the surface phi equals to c. So I hope you can remember from basic calculus that if this is a curve and then we have a tangent through this curve, And then this is what we call the normal. So this is the tangent. So these two are meeting at 90 degrees. So because of this condition here, that gradient of phi dot dr equals to 0, then the two are tangent to each other. So it means that then the normal, this gradient of phi is normal to the surface given by phi equals to c. So if we let this gradient of phi be given by magnitude of gradient of phi times the normal vector, unit normal, then also let be the perpendicular distance So actually, this is not a vector, so we can just, from this diagram here, because we are denoting that one to be a distance. So this is what we are calling this gap perpendicular distance, this dn. It's not a vector. So dn to be the perpendicular distance. So there's no arrow here. Between the two level surfaces. Then the rate of change of this surface phi, or this function phi in the direction is simply given by partial phi partial n. And we know from calculus that the phi dn is given by limit as delta n approaches 0 of delta phi over delta n, which is the same thing as now limit as delta n approaches 0 of gradient of phi times or dot delta dr over this delta n. So which can be written as limit as delta n approaches 0 of magnitude of this gradient of phi times the unit normal vector dotted with dr divided by delta n, which can be written as limit as delta n approaches 0 of gradient of phi magnitude dn over delta n, which is just the same as magnitude of gradient of phi. Please note that n dotted with the r is the same as magnitude of n times magnitude of this delta r So remember this delta r, delta r cosine of theta, which is the same as magnitude of delta r cosine of theta, which is the same as the n. Now remember, this is because theta is 0 in this case. So this is what is making us to make this simplification. So therefore, magnitude of gradient of phi is the same as partial n, partial phi, partial n. Hence, gradient is a vector normal to the surface, phi equals to c, and has a magnitude equal to the rate of change of phi along this normal. So that's what we have. So there's what we call directional derivative. So normal and directional derivative. So for normal, so if I represents a family of surfaces, on differentiating this function but we know that this is given by the dot product of gradient of phi and the r. So which means gradient of phi dotted with, dotted with the r gives 0. Because remember, when you differentiate a constant, say you get 0 on this right-hand side. So the scalar product of the two vectors remember, dot product is also called scalar product. Because the dot product of these two vectors results into a value of 0, then they must be perpendicular. That's definition of perpendicular vectors. That when you dot them, you always get 0. So the r in the direction is the direction of tangent to the given surface. Thus, gradient of phi is a vector normal to the surface phi equals to c. So that we have the definition of normal vector. And lastly, the directional derivative. So the component of this vector grad of phi in the direct is a vector the direction of a vector d actually this d is a unit vector of a unit vector. So unit vectors, we represent them. This should be cup. This is a cup, and it's called the directional derivative of phi. That unit vector D. So if we define then but this is a vector. So this is how we define those quantities. So the easiest way is to simply define a direction derivative to be the dot product of gradient of phi and a unit vector A. And the direction of A determines the direction of the vector you find by dotting grad of phi and this new vector D. So finally, gradient of phi is the maximum rate of change of phi. So now we'll give examples on how to interpret a gradient, both from geometrical point of view and physical point of view in the next series. Thank you.